Welcome to this explainer. Today, we're tackling a make or break skill in engineering research, how to transition from just summarizing the literature to actively identifying trends and articulating your own specific research gaps. If you've ever felt like you're just listing off what other people did without actually pinpointing where your own work fits in, you are definitely in the right place. We're moving way beyond that basic paper A did this, paper B did that summary, and we're going to learn how to interpret those previous studies to find your unique starting point.
Here's our roadmap for today. We'll cover trends versus research gaps, how to actually identify those trends, the 4 types of gaps, finding those gaps from limitations, and finally, writing that killer gap statement.
All right, part 1, trends versus research gaps. Let's get right into the difference.
So this is probably the most common point of confusion. Think of a trend as where the whole field is migrating. What researchers are increasingly focusing on over time, like the massive surge in deep learning models for robotic vision. A gap, on the other hand, is what's left behind. It highlights what is still insufficiently solved despite that trend, like a lack of lightweight models for low-cost systems. You can have a ton of trending activity in a specific field, but it can absolutely still contain huge critical gaps.
Moving to section 2, identifying research trends. It's all about spotting the patterns.
To find these elusive gaps, you kind of have to zoom out and look at the broader landscape of your literature. Take the timeline of battery management systems, for instance. Back in 2021, the big focus was traditional machine learning. By 2022, neural networks started taking over. 2023, it was all deep learning. And now in 2024, we're heavily leaning into hybrid AI models. When you map it out like this, you can literally see the field evolving.
But listen, a trend isn't just a popularity contest, right? It's about understanding precise engineering trade-offs. Take convolutional neural networks, or CNNs. They give you incredibly high accuracy, but man, they require massive data sets. YOLO models, lightning-fast real-time detection, but they might completely miss small objects. And traditional vision methods are great for low compute power, but they're just not as adaptable. Understanding a trend means recognizing that performance isn't just about raw accuracy. It's speed, it's cost, it's complexity, and it's energy consumption.
Which brings us to section 3, the 4 types of gaps. Finding what's missing.
Now, a research gap isn't just waving your hands and saying, hey, nobody has studied this topic. I mean, if literally no one has studied it, there's probably a very good reason for that. Instead, finding a gap requires asking what specific, tangible problems are still unsolved right in the middle of this trending literature. The secret is that the gaps are almost always hiding inside the limitations of the current study.
To make this a whole lot easier, these unsolved problems usually fall into 4 distinct buckets. This is basically your mental map for engineering research: technical gaps, methodological gaps, application gaps, and data gaps. Let's break down exactly what each of these looks like in the real world.
First up, the technical gap. This happens when existing systems hit a hard technical wall. Like, say you've got an AI model that's incredibly accurate, but it requires a supercomputer to run on. That massive compute requirement is a technical constraint, and it screams for a solution, like developing a lightweight model that maintains accuracy but uses way fewer resources.
Next, the methodological gap. You see this when the evaluation methods just aren't rigorous enough for real-world engineering. You know the drill. 10 different papers prove an algorithm is flawless, but wait, every single one of them relied entirely on computer simulations. The methodological gap there is the glaring lack of physical, real-world experimental testing.
Then there's the application gap, which is just everywhere in engineering research. It's when a piece of tech works beautifully in a pristine, climate-controlled lab setting, but it hasn't survived the chaos of dynamic industrial conditions. If a robotic vision system only works perfectly when the lab lighting never changes, there is a massive application gap just waiting to be filled by testing it on a messy, unpredictable factory floor.
And fourth, the data gap. This one's pretty straightforward. The data being used to train or test models is either way too small or just lacks the necessary diversity. If every single researcher is training their AI on the exact same limited data set, well, that's a huge data gap. It presents a clear opportunity for you to step in and build a much larger, more diverse data set.
All right, section 4, find in gaps from limitations. Let's connect some dots. So how do you systematically find these gaps? You do it by connecting the dots across multiple papers. Let's say paper A was only tested with lab data. Paper B was tested under really limited environmental conditions, and paper C, tiny data set. On their own, they are just isolated observations, but when you put them all together, a powerful pattern starts to emerge.
When you synthesize those individual limitations, an overarching gap just jumps right out at you.
By combining those points, we can confidently state, existing AI-based battery models require further validation using diverse, real-world conditions. See what we did there? You just moved from summarizing to synthesizing. You found an exact, evidence-based starting point for your own original contribution.
Finally, Section 5, Writing the Gap Statement. It's time to articulate the need. Now, your gap statement has got to be specific and totally grounded in evidence. We absolutely must ditch those weak, vague claims like, more research is needed in this area. I mean, that tells the reader nothing. Compare that to a strong, detailed statement. Although deep learning models have improved accuracy, most are evaluated under controlled laboratory conditions. Further research is required to validate these systems in dynamic industrial environments. Boom! It details exactly what the literature has achieved and exactly what it is missing. To get that professional, evidence-based statement every single time, just follow this highly logical three-step formula. Step 1, state the existing knowledge. What has the field achieved so far? Step 2, highlight the limitation. Where do those achievements actually fall short? And Step 3, articulate the need. What specific research needs to happen right now to bridge that gap?
Let's see this formula in action. Step 1, previous studies have investigated AI-based fault detection methods. There's your existing knowledge. Step 2. However, many approaches are evaluated using limited laboratory datasets. Okay, there's the limitation. And Step 3. Therefore, further research is required to develop robust systems suitable for industrial environments. That is the specific need. It's incredibly logical, moving right from what we know to the limitation and ending on a targeted call to action.
So, as we wrap up this explainer, I want you to grab your own literature extraction tables and put this to work. Find the trends, categorize the limitations into technical, methodological, application, or data gaps, and start connecting the dots. Synthesize that information. I'll leave you with this thought to mull over. When you look at the current literature in your specific field, what is the exact limitation that's going to drive your very next engineering breakthrough?